Today I'm going to describe what happens to the domain and range of a logarithmic function under a vertical reflection. First of all, in the vertical flip of a logarithmic function, we consider a general logarithmic function expressed as y equals logarithm base ax, where base a can be any positive number greater than 1. Now let's see what happens to the domain of definition and range when the function flips vertically. Let's take y equals logarithm x as an example. First, by flipping vertically, the logarithm function becomes y equals negative logarithm x, and the minus sign in front of the function indicates the flip. This change is important because it affects the properties of the function. In this process, the domain of the function changes relatively little. The domain of the original logarithmic function includes the positive value x because logarithmic functions are only defined as possible numbers. When we do a vertical flip, the domain stays the same. Therefore, the domain of the flip function is still the set of positive numbers. However, an important change occurs within the scope of the logarithmic function. We can see this change graphically. The following figure shows the blue parent function y equals logarithm x and the yellow reflection function y equals negative logarithm x. As can be seen from the figure, the domain of both functions is 0 infinite, but their range is different. It's the scope of y equals logarithm x values negative infinite, and y equals negative logarithm x is the negative infinite 0. When we compare the original function y equals logarithm x with the flip function y equals negative logarithm x, we can see that the function plot flips vertically on the x-rays. The flip of the logarithmic function causes all points on the graph to be symmetric above or below the x-rays. In other words, flipping changes the sign of the function value, but it does not change the overall shape or pattern of the function. Therefore, the range of the flip function is a set of negative numbers. To sum up, when a logarithmic function is flipped vertically, its domain remains unchanged, still a set of positive numbers, while its range changes to become a set of negative numbers. This explanation is supported by our previous chart and helps us better understand how the function changes under vertical flipping. Now let's talk about question 2. A logarithmic function is typically represented as fx equals log base b of x, where b is a positive constant greater than 1. The logarithmic function has a characteristic shape with an asymptote, a vertical line that the graph approaches but never touches at x equals 0. The domain of the logarithmic function is all positive real numbers, and the range is all real numbers. Let's talk about the first one, horizontal translation. A horizontal translation of a logarithmic function shifts the graph horizontally to the left or right. Suppose we have a logarithmic function fx equals log base b of x. If we replace x with x minus h, where h is a positive constant, the graph will shift h units to the right. On the other hand, if we replace x with x plus h, the graph will shift h units to the left. Let's consider an example where we have the function fx equals log base 2 of x. The graph of this function is shown at the red one. Now let's apply a horizontal translation by replacing x with x minus 1. The resulting function is gx equals log base 2 of x minus 1. The graph of gx will be shift 1 unit to the right. As you can see, the graph of gx equals log base 2 of x minus 1 is shift 1 unit to the right compared to fx equals log base 2 of x. The domain remains the same, but the graph is translated horizontally. Now let's talk about vertical translation. A vertical translation of a logarithmic function shifts the graph vertically up or down. If we replace y with y plus k, where k is a positive constant, the graph will shift k units upward. Conversely, if we replace y with y minus k, the graph will shift k units downward. Let's consider the same function fx equals log base 2 of x. The graph is showing in red. Now let's apply a vertical translation by replacing y with y plus 1. The resulting function is gx equals log base 2 of x plus 1. The graph of gx will be showing in green one. As you can see, the graph of gx equals log base 2 of x plus 1 is shift 1 unit upward compared to fx equals log base 2 of x. The range remains the same, but the graph is translated vertically. In summary, a horizontal translation of a logarithmic function shifts the graph left or right without changing the domain, while a vertical translation shifts the graph up or down without changing the range. Let's begin with the question 3. First, we need to graph the function fx in purple and y equals x in red. Then we need to graph the inverse function of the fx in the line y equal x. So we need to know what is the inverse function is. We can use these steps to calculate it. Step 1. Replace fx with y. Then we can swap x and y. and then we can solve the equation for y. Then we will have the inverse function. We need to graph it in blue. Now we need to know the domain, range, and asymptote of this function. The domain of the inverse function is determined by the original function f(x). In the original function, the logarithm is defined only for positive values of x. Therefore, the domain of the inverse function f of x is all positive real numbers. The range of the inverse function of f of x is determined by the behavior of the original function f(x). The original function is a logarithmic function and its range is all real numbers. Since the inverse function is the reflection of the original function across the line y equals x, the range of inverse function is also all real numbers. And the asymptote. The equation of the asymptote for the inverse function can be determined by examining the behavior of the original function's asymptote. The original function f(x) has a vertical asymptote at x equals 0. When reflected across the line y equals x, asymptote. The equation of the asymptote for the inverse function can be determined by examining the behavior of the original function's asymptote. The original function f(x) has a vertical asymptote at x equals 0. When reflected across the line y equals x, this vertical asymptote becomes a horizontal asymptote. Therefore, the equation of the asymptote for the inverse function f of x is y equals 0. The question D is determine an equation for the inverse of x, f of x. We can do it step by step. The first one is we can distribute the exponent of 2 to the terms inside the since 10 to the power of a is a constant value. Let's denote it as a new constant, such as a equals 10 to the power of 8. So we have this. So the equation can be rewritten as f(x) equals a to the power of 2x, where a is a constant equal to 10 to the power of 8. This form of the equation represents an exponential function, where the base a is a positive constant greater than 1. The function increases rapidly as x increases, reflecting exponential growth. The significant value of a will determine the rate of growth and the infinite value of the function.